In 80 AD, the Emperor Titus opened the Colosseum in Rome with 100 days of continuous games. 50,000 people filled the seats every day for 100 days. They arrived, they watched, they left, and the next 50,000 came in. In a city without cars, without electric lighting, without modern crowd management technology, without computers, without any of the infrastructure that modern stadiums consider essential, the Romans moved 50,000 people in and out of a single building so efficiently that modern crowd flow engineers have studied the system and found that it outperforms the entry and exit systems of most contemporary sports stadiums. This is not the most impressive engineering fact about the Colosseum. It is not even close. The building was constructed in 8 years. 8 years for a structure that used more stone than most medieval cathedrals built over centuries. 8 years for a building with a concrete foundation so sophisticated that modern materials scientists spent decades trying to understand it and only recently discovered why it has lasted 2,000 years. 8 years for a hydraulic system, a lifting mechanism, an acoustic engineering solution, and a crowd management infrastructure that the modern world did not fully replicate until the 20th century. The Colosseum is not a ruin. It is a masterpiece of engineering that has been partially dismantled by time and by people who did not understand what they were destroying. What remains is enough to prove that the people who built it understood physics, materials science, hydraulics, acoustics, and crowd psychology at a level that the Western world would not reach again for 1,500 years. This is the story of how they did it. The foundation of the Colosseum sits on what was once a lake. The Emperor Nero had drained an artificial lake on this site to build his private palace complex, and when the Flavian dynasty decided to build the amphitheater here as a gift to the Roman people, their engineers inherited a foundation problem that would defeat most modern construction projects. Building a structure of this scale on former lakebed soil requires managing the settlement of the ground under enormous weight. Modern engineers handle this with deep pile foundations, reinforced concrete, and sophisticated soil analysis. Roman engineers in 70 AD had none of these tools. What they had was a concrete formula that the modern world has spent considerable effort trying to understand. The foundation of the Colosseum was poured in a single continuous ring of Roman concrete, what the Romans called opus cementitium, approximately 13 meters deep and 52 meters wide at the outer edge. This concrete contained volcanic ash called pozzolana sourced from the region around Naples, combined with seawater, lime, and aggregate materials including rubble and broken pottery. The behavior of this concrete under stress is the opposite of modern Portland cement concrete. Modern concrete reaches its maximum strength within approximately 28 days of curing and then begins a slow process of degradation as water and chemicals penetrate its structure over decades and centuries. Roman concrete made with pozzolanic ash does not behave this way. The chemical reaction between the volcanic ash, the seawater, and the lime produces mineral compounds called tobermarite crystals that continue to grow within the concrete matrix over centuries, actually increasing the material's compressive strength over time rather than decreasing it. A study published in 2017 in the journal American Mineralogist by a team from the University of California, Berkeley analyzed samples of ancient Roman marine concrete structures and found that after 2,000 years, the concrete was stronger than when it was poured. The crystals had continued forming for 2 millennia, filling microscopic cracks and voids that would have weakened modern concrete into rubble. The engineers who designed the Colosseum's foundation did not know the chemistry behind this. They knew the result. Roman builders had been using pozzolanic concrete for over a century before the Colosseum was built and had observed empirically that structures built with this material in marine and wet environments lasted longer and performed better than those built with other materials. They used what they knew worked even without understanding precisely why it worked. The result is that the foundation of the Colosseum has been supporting the weight of the remaining structure, now reduced to perhaps a third of its original mass, for 2,000 years on former lakebed soil. Modern geotechnical engineers who have analyzed the site have concluded that the foundation continues to perform within acceptable parameters. A foundation designed without computers, without soil science, without modern materials engineering, is still doing its job 2,000 years later. Beneath the arena floor of the Colosseum, which no longer exists as visitors to the site see the exposed substructure beneath, there was a mechanical system that had no equivalent anywhere in the ancient world and would not be replicated in complexity until the development of modern theater stage machinery in the 19th century. The hypogeum, the underground level of the Colosseum, was a 2-story network of tunnels, corridors, animal holding pens, and machinery spaces covering the entire footprint of the arena above. It was built to solve a single problem: how do you get wild animals, gladiators, elaborate stage sets, and sometimes entire trees and landscape features onto an arena floor in front of 50,000 spectators without the audience seeing how they got there? The answer was a system of vertical lifts. At least 28 elevator shafts have been identified in the hypogeum, each capable of raising a platform from the lower level to the arena floor above. These were not simple rope and pulley systems. Each lift was a counterweight mechanical assembly operated by teams of workers below, capable of raising a loaded platform of several hundred kilograms smoothly and quickly enough to create the theatrical effect of animals and fighters appearing suddenly from beneath the earth. The coordination required to operate this system is staggering. Ancient accounts describe events at the Colosseum where dozens of animals appeared simultaneously from different points across the arena floor. This required not just functioning lift machinery but synchronized operation of multiple independent mechanical systems by teams of workers who could not see the arena above them and could not see each other, coordinating their actions based on audio cues and a pre-planned sequence of operations. Ancient sources describe a single opening event at the Colosseum where 100 lions appeared on the arena floor simultaneously. Based on the identified lift positions and the dimensions of the shafts, engineering analysis suggests this was physically achievable with the documented hypogeum infrastructure. It required precise timing, pre-positioned animals in the correct shafts, and coordinated release mechanisms operated by multiple teams in the dark below the arena. The hydraulic system connected to the hypogeum is equally remarkable. The Colosseum was connected to Rome's aqueduct network, which delivered water at sufficient pressure and volume to flood the arena floor to a depth of several feet within a period measured in hours. Ancient sources describe naval battles staged in the Colosseum with actual boats on actual water. Modern hydraulic engineers who have analyzed the documented water flow rates from the Roman aqueduct system and the dimensions of the Colosseum arena have confirmed that this was physically possible with the documented infrastructure. The drainage system that removed the water was equally engineered. A network of drainage channels beneath the hypogeum connected to Rome's sewer system, the Cloaca Maxima, allowed the arena to be drained and returned to dry condition after aquatic events. The Romans could flood the arena, stage a naval battle, drain it, and have gladiators fighting on a dry sand floor in the same day. The Colosseum had 80 entrances. Not 80 gates in the outer wall. 80 numbered and designated entry points, each connected to a specific seating section through a dedicated internal corridor and stairway system that did not intersect with the corridors serving other sections. This system, which the Romans called the vomitorium system from the Latin word meaning to discharge rapidly, was designed so that every person in the stadium could reach their assigned seat from the exterior of the building without passing through any space used by people going to different sections. Once inside, the system worked in reverse, allowing 50,000 people to exit the building simultaneously through 80 separate streams without any of those streams converging until they reached the exterior plaza. Modern crowd flow engineering was formally established as a discipline in the late 20th century following a series of stadium disasters caused by crowd compression and panic. The principles that emerged from this research: separation of entry and exit flows, elimination of cross-flow between crowd streams, sufficient corridor width per person per minute of flow, adequate holding capacity in pre-entry spaces. All of these principles are present in the Colosseum's design. A study conducted by researchers at the University of Southern California applied modern crowd flow modeling software to the Colosseum's documented layout and found that the theoretical evacuation time for 50,000 people using the vomitorium system was approximately 15 minutes. The same modeling applied to several contemporary sports stadiums of similar capacity produced evacuation times ranging from 20 to 45 minutes. The Roman engineers who designed this system had no crowd flow software. They had no formal discipline of crowd management. What they had was the accumulated experience of managing very large crowds in Roman public spaces over many generations, combined with an intuitive understanding of human movement patterns that produced a solution that modern engineering has not substantially improved upon after 2,000 years. The seating allocation system was equally sophisticated. The Colosseum's 50,000 seats were divided into sections corresponding to social rank, profession, gender, and citizenship status. The emperor and the Vestal virgins had dedicated boxes at the arena level. Senators sat in the lowest tier. Knights in the next tier. Male citizens in the upper tiers. Women and the poor at the very top. Each social category had its own designated entry points, its own corridors, and its own staircases, so that a senator arriving at the Colosseum never shared physical space with a common citizen from the moment of entry to the moment of departure. This was not merely a social hierarchy enforced in the seating arrangement. It was a crowd management solution. By separating groups with different arrival times, different departure behaviors, and different expectations about personal space and movement, the Romans reduced the friction points in the crowd flow system that create dangerous compression and panic. The Colosseum was an outdoor structure with no roof over the seating area. 50,000 people sitting in an open oval under the Roman sky with a sand arena below them. Modern acoustic engineering would predict that meaningful sound projection in such a space would be impossible. The ambient noise of 50,000 people, the wind, the sounds of the city around them, should have made it impossible for any voice from the arena floor to be heard clearly at the upper tiers 50 meters away and 30 meters above. The acoustic properties of the Colosseum are not accidental. The geometry of the seating bowl, the angle of the seat tiers relative to the arena floor, the surface materials used in the construction of the seating areas, and the height and curvature of the outer walls all contribute to an acoustic environment that focuses sound from the arena floor toward the seated audience. Acoustic engineers from the Georgia Institute of Technology conducted a study of the Colosseum's acoustic properties using computer modeling based on the documented dimensions of the structure. Their findings, published in the Journal of the Acoustical Society of America, confirmed that the geometry of the Colosseum produces a measurable focusing effect on sound originating at the arena floor level. A person speaking at the center of the arena at normal conversational volume would be heard at the upper tiers at a sound level significantly higher than the open-air baseline would predict. The velarium, the enormous retractable canvas awning that covered the seating area of the Colosseum during events, contributed an additional acoustic effect. When deployed, the velarium created a partial enclosure above the seating bowl that reflected sound downward toward the audience rather than allowing it to dissipate upward into the open sky. The velarium was not designed as an acoustic device. It was designed to shade 50,000 spectators from the Roman sun. But its acoustic effects were understood and valued by the Romans who attended events there. The velarium itself was an engineering achievement of the first order. It covered approximately 2/3 of the seating area when fully deployed, an area of roughly 6,000 square meters of heavy canvas. It was supported by a system of wooden masts fitted into stone sockets visible at the top of the outer wall, with a network of ropes, pulleys, and rings that allowed sections of the covering to be deployed, adjusted, and retracted by teams of sailors from the Roman naval base at Misenum who were permanently stationed in Rome specifically for this purpose. Managing 6,000 square meters of canvas above 50,000 people in variable wind conditions requires sophisticated understanding of load distribution, anchor point placement, and the behavior of large flexible structures under dynamic loading. The sailors who operated it had this understanding from their professional experience at sea. The engineers who designed the anchor system had to translate that maritime knowledge into a permanent architectural installation. The result was a retractable shade structure of a scale that was not built again until the development of modern stadium roof technology in the late 20th century. The Colosseum was built in 8 years. This single fact contains within it the full measure of what the Romans achieved. The structure required approximately 100,000 cubic meters of travertine limestone for the outer walls alone. This stone was quarried at Tivoli, 30 kilometers from Rome, cut into blocks averaging several hundred kilograms each, transported to the construction site by ox cart along roads that the Romans themselves had built, and lifted into position using a system of cranes and lifting equipment that was itself an engineering achievement requiring skilled operation. The concrete foundation required volcanic ash from the Phlegrean fields near Naples, approximately 200 kilometers from Rome by the most direct route. The logistics of supplying a construction site of this scale with materials sourced from locations across central Italy, while simultaneously quarrying, shaping, and placing the stone, while simultaneously manufacturing the iron clamps that held the stone blocks together, while simultaneously training and managing a workforce estimated at tens of thousands of people, represents a project management achievement that has few parallels in human history. Before the Industrial Revolution, the project was completed on schedule. The Colosseum opened in 80 AD, 8 years after construction began in 72 AD under the Emperor Vespasian. It opened with the full complement of engineering systems operational. The lifts worked. The drainage worked. The crowd management system worked. The Valerium was installed and operated by its naval crew. 50,000 people attended on the opening day and the building performed as designed. Modern construction projects of comparable complexity and scale routinely exceed their planned timelines by years. The Sydney Opera House, a structure of comparable architectural ambition, took 14 years to build instead of the planned 4 and cost 15 times its original budget. The Big Dig Highway project in Boston took 16 years instead of the planned 5. Large modern infrastructure projects with computers, project management software, modern materials science, and centuries of accumulated construction knowledge regularly fail to deliver on time and on budget. The Romans built the Colosseum in 8 years without any of these advantages. They built it on former lakebed soil using a concrete formula they understood empirically but not chemically. They built a mechanical system beneath the arena that had no precedent anywhere in the ancient world. They designed a crowd management system that modern engineering has not substantially improved. They installed an acoustic environment that focused sound across 50 meters of open air. And they opened on schedule. The question that this raises is not how they did it with such primitive tools. They did not have primitive tools. They had Roman engineering, which was sophisticated, empirical, systematic, and capable of achievements that the world would not see again for 15 centuries. The question is what else they knew that we have lost and are only now beginning to rediscover. The Colosseum today is half of what it was. The stone is gone, recycled into the churches and palaces and bridges of Rome. The marble facing is gone. The Valerium masts are empty sockets in the top of the outer wall. The arena floor is gone, exposing the hypogeum below to the open sky for the first time in 2,000 years. What remains is enough. The foundation is still performing. The crowd flow system still works for the millions of tourists who visit each year. The acoustic properties are still measurable. The engineering is still there in the geometry of what survives, waiting to be read by anyone who looks carefully enough. The people who built it in 8 years with ox carts and volcanic ash and empirical knowledge accumulated over generations were not primitive. They were not lucky. They understood what they were doing with a clarity that produced results that the modern world spent 15 centuries trying to replicate. The Colosseum is not a monument to the glory of Rome. It is a monument to what human beings can achieve when they apply systematic intelligence to an engineering problem without the assumption that it cannot be done. Subscribe. Because the Romans left other buildings behind. And every one of them contains engineering that the history books have not fully explained yet.